All right, what I want to do to begin with today is to go over questions on homework, and I have a few questions that some people had trouble with that I definitely want to cover. But I think maybe what we'll do is we'll start with any questions that those of you who are here right now want to take a look at from the homework set. So, are there any questions that stand out from the homework that were difficult?
Could you go over question 8 from 2.1?
Yeah. Okay. All right. So is this the question you were looking at?
Yeah.
Okay. So find the area of the region enclosed by y equals 2.25x and x equals 9 minus y squared. So they've given us a graph here. What we want to do when we're looking at area between two curves, we typically want to start by figuring out, is it easier to think of this area, when we think of area under a curve, right, we fill up with rectangles, is it easier to think of the rectangles going vertically or horizontally? And if we're given a graph, it's usually a lot easier just to kind of visually inspect, right? So here, if I make my rectangles go up and down, then the bottom part of my rectangle and the top part of my rectangle are bounded by the same curve, which is weird. And it's also going to, have a transition point, right? Because here it's two different curves and over here it's the same curve. And so I'm gonna have to break things up. If I go left, right, then the left side is always the line and the right side is always the parabola. And so that makes things a lot simpler. Okay, so that's going to be the way that we want to go. I'm gonna think about the rectangles as going this way. Okay, so that means that I want the equations as x equals a function of y. So I want both of my equations to be x equals f of y. Okay, and one of them is already set up nicely for that, right? So the quadratic is already solved for x. What we want to do then is just solve the other one, right? So I divide by 2.25, right? So I can say, all right, this line over here is going to be x equals 1 over 2.25 y. Okay. The next thing that we need to do before we start setting up an integral or anything like that is we need to figure out where it starts and stops. So I want to find the intersection points. Right? So here, this is going to be where x and y are the same on both curves. So if I have x equals a function of y for the first curve and x equals a function of y for the second curve, then I want to see what y value can I plug in to get the same x. So if x is the same and x is 9 minus y squared and x is also 1 over 2.25y, then I set those two equal to each other and I solve for y. Okay. This has a y squared in it, so now I need to solve this quadratic. Okay, so I'm just going to add y squared and subtract 9 to get 0 equals y squared minus 1 over 2.25y. And you don't need to leave it as 1 over 2.25 if you want to rewrite that as a decimal, that's fine. Or you could convert it to another fraction. So then to solve this quadratic, I'm just going to use the quadratic formula. Now you could multiply and get rid of all your fractions, but at this point I think it's going to be faster just to use the quadratic formula. Okay, and I don't want to keep writing this this 1 over 2.25. Okay, it would probably work best if I convert that to to a fraction, and then when I take its reciprocal, I have a new fraction. Okay. If you wrote that as a decimal, that wouldn't be too terribly bad either. Okay. So if you write this 1 over 2.25 is like 0.4 repeating, then, you know, typically if we're getting a, you know, a numerical answer at the end, that's going to be all right. I mean, obviously the more mathy way to do things is to write a fraction, but I think we'll just try this out and see if I get too much error. Oops, y equals y, that doesn't make sense. Let me, okay. So I'm writing the quadratic formula here. So I want the opposite of b. So this value is 0.4 repeating, right? So I want the opposite of negative 0.4 repeating, so I'm going to get 0.444. Okay, so that's negative b plus or minus the square root of this b value squared minus 4 times a, which is 1, times c, which is negative 9. All over 2 times a, which is 1. Okay. And at this point, I think that we can plug this into our calculator.
Too, bro.
What's that?
Look at it.
All right. So here I'm going to get, when I use the positive, y equals 3.23, and when I use the negative, I get negative 2.79. I want to be a little bit careful. Maybe I'll take a couple extra decimal places out. So those y values are going to be our limits of integration. So then the area between the two curves is going to be the integral from y equals negative 2.786, y equals 3.230, and then I'm just going to take the difference of the curves. Now what we typically want to do is take the right side minus the left side. If we get them mixed up, we'll just be exactly off by a negative. Okay, so it's not too big a deal. Okay, the right side is the parabola, so that's 9 minus y squared. And then we subtract the left side, which is the 1 over 2.25y. One of the things that I like to do is put the first function in parentheses and the second function in parentheses so that we don't make a mistake distributing a negative. In this case, we wouldn't anyway, because this you know, that line is just one term, but it's a good practice. And integrating dy. Okay. So we get 9y minus 1/3 y cubed minus our same constant. And then when I integrate y, I get 1/2 y squared. And then all we have to do is plug in. Okay. Okay, does that make sense?
Yeah, it helps. Yeah.
Okay. Any questions about where like these pieces, like we did these pieces, but I didn't show which one goes where, right? So the C is this value and the D is this value, right? And then this integral here that we set up is this answer, and then the number that it spits out is the area.
Yeah, it was just a little confusing watching the videos and then trying to understand it, I guess. So
Yeah, that's fine.
I did have another question
Okay.
about 2.2. I was curious on how you find the bounds of the definite integral when you're solving for the volume.
Okay, let's come to that. Let's do the rest of the 2.1 questions first, because somebody else in the chat asked another 2.1. So then we'll get to the 2.2, but I definitely want to answer that. Okay, so then 2.1, Shabam, you said the sixth sum.
Yeah.
Is that this one?
Yes.
Okay. See if I can make that a little bigger for you. There we go. Sketch the region enclosed by the curves, decide whether to integrate with respect to x or y, then find the area of the region. Okay, so I'm going to try to just freehand graph this and see where we end up. So the first curve is 2y equals 5 root x. Okay, so if I want to graph that, I think it's really easy for me to solve for y. So y equals 5 halves root x. And then I can graph that, right? So that's just a root x equation, maybe stretched a little bit up. Okay. And then now let's look at the next one. The next one is y equals 3. That's just going to be a horizontal line. Okay, and then the last one is 2y plus x equals 6. Again, I think that it's probably easiest for me to solve for y here, but I could just as easily solve for x. Actually, it's probably easiest to solve for x, but we're used to seeing things as y equals, and the first two we wrote as y equals, so I'm just going to solve for y. So 2y equals negative x plus 6, so y is negative 1/2 x plus 3. Okay, so I have an intercept here at 3 and a negative slope, so this is going to just go down. All right, sketch the region enclosed by the curves. So we want a region that's enclosed by these 3 curves, and that's maybe a little bit difficult at first because you see like a lot of different intersection points. But if I look at this little area here, right, that has the green one is the top, the blue one is one side, and the red one is another side. So that's enclosed by all 3. If I look at any other region, it's not really enclosed. Like up here, it goes up forever. Here, it goes to the right forever. It goes out forever. All the rest of these regions aren't enclosed. They just kind of keep going. So this is the space that's enclosed by those 3 curves. Because I'm writing each of these 3 curves as a y equals, I think it's going to be easier to integrate with respect, with going up, down. Except that if I do that, I have a switching point in between. Okay, so if I wanted to integrate with respect to x, then my rectangles go up, down, and I'm going to start here, and then I'm going to integrate till I get to that point, and then I have to switch and use a different integral from this point to the end. Okay, so it's going to take 2 integrals. If I go left, right, because I have a perfectly straight line here, right, a horizontal line, I'm going to start at whatever this intersection point is, and then go up until y is 3, and I'm only integrating between 2 curves. So I can get it all done in one integral. Okay. And then the only thing I have to do is resolve these and write an x equals. Okay. So the reality is that you can do this either way, right? Both of them will be a way to integrate. It's just a difference of what kind of work do you want to do? Okay. So I don't know. I guess we could take a vote on which one you want to do. I'm not sure that it makes too much of a difference either way. But since I've already solved these for y, we could just stick with the y ones, although that one's more work. Either way, we're going to have to find this intersection point between my red curve and my blue one. So let's go ahead and solve for that. So the intersection point is going to be where 5/2 root x is equal to -1/2 x plus 3. To solve this equation, I need to square both sides. So when I square the left, I'm going to get 25/4 x. And when I square the right, I need to FOIL that out. So -1/2 x times -1/2 x is a positive 1/4 x squared. And then I'm going to have a -1/2 x times 3. And then another -1/2 x times 3. And then the 3 squared. So grouping those terms all together, we get 1/4 x squared minus 3/2 x minus another 3/2 x. And then I want to subtract the 25/4 x from both sides to gather my like terms. Okay, so maybe just doing this a little bit mentally, I'm going to have -6/2, which is -12/4, and then when I subtract 25/4, I'll have -37/4. Hopefully. If I did my arithmetic wrong, please double check me on that. Okay, I don't like to have all of these fractions, and since my denominator is 4 for all the fractions, it's not necessary, but I'm just going to multiply everything by 4. And this is a much nicer looking quadratic that I have to solve. Okay, and you can solve by factoring, or you can use the quadratic formula, whichever one you like. I think that this one will actually factor pretty nicely after we get rid of the fractions. It's easy to see. Okay, x minus 36, x minus 1. So x minus 36 equals 0. Get 36. X minus 1 equals 0, and I get x equals 1. Okay, looking at my graph, we probably want this x equals 1. And what we really want to do is make sure that this is actually solving it, right? So if I plug 36 in for x, okay, when I plug into my square root function, I'm going to get 5/2 times the square root of 36, which is 5/2 times 6, which is like 30. When I plug in 36 over here, -1/2 times 36 is -18 plus 3 is -15. So that doesn't work at all. This isn't a real solution. When we square both sides of an equation and create a quadratic, sometimes we introduce a fake solution. Okay, and really what's happening is when I square both sides, this was a square root function. When I turn it into, when I square both sides, I effectively make it into like a parabola. Okay, and so what we're doing is finding an intersection out here that doesn't exist with our original functions. When I plug 1 in, though, here I'm going to get 5/2. Here, when I plug in 1, 3 minus 1/2 is 5/2. That one does work. Okay, so this is the point 1, 5/2. Okay, if I integrate with respect to y, right? If I do everything horizontally, then I don't need to do any more solving for points, because I can just start at a y value of 5/2 and go up to a y value of 3, and I'm done essentially, right? So I'm done setting things up. So I think I actually prefer that. So I'm going to start at y equals 5/2 and go up to a y equals 3. And then my right function is this square root function. Okay. I need to solve for x. Okay, so 4/25 y squared equals x, right? And then the bottom function is that line, so I want to solve that one for x, right? And if I just subtract, I'll get x equals negative 2y plus 6. Okay, and then I'm good to go, right? So then we can say, all right, I'm integrating from 5/2 to 3. I have 4/25 y squared minus a negative is plus 2y minus 6. Okay, and then we integrate. 4/25 hangs out. 1/3 y cubed plus 2 times a half y squared. And then we just have to plug in and compute. Okay, does that one make sense now?
Yeah, thank you.
Okay. Like I said, that's not the only way to do this problem. You can also set this up, you know, with your rectangles going vertically, right? And then we would integrate from 0 to 1, where I take the integral of 3 minus, you know, this equation, plus the integral from 1 to whatever this intersection point is. So we'd have to solve for another intersection point. And then we would take, you know, 3 minus this function for our integral. Okay, so I just think that dy is a little bit easier. Anything else from section 2.1? Okay, before we move on, there was another question that I was asked earlier. This window problem. Okay, this is a tough problem, and the saving grace is that the question sort of walks you through what some of the steps are. Now, there's more than one way to set this problem up, but again, the problem has sort of told you a way to set it up and you know, guided you in one direction, and so we'll kind of continue from there. So here's the question. A window has the shape of a parabola, so this top curve is a parabola. Above a circular arc, so this curve is a circle. Okay, and they give us the radius of that circle. Okay, find the area of the window. So find the area that's enclosed here. And what they're doing is they're saying use this dotted line as your x-axis and this solid gray line as your y-axis. So this would be the origin right here. That's not the only way to set it up, but you know, if they're going to give us a little bit of help setting things up, then we'll, you know, continue on from there, and that works fine. Another way to set things up is you know, make the center of the circle your origin, and that might help too. But that makes the circle easier, but it makes the parabola more complicated. So I think that the setup that this question is sort of forcing you into is trying to make the most difficult part of the problem a little bit easier. So I kind of like that. All right. Let's maybe just look at a little bit of basic geometry and kind of figure out what we know. This point, knowing something about this point is going to be really helpful because I know the distance between these 2 points is 11.2 feet. Okay, and this is the top of a circle, which is symmetric. It's the top of a parabola, which is symmetric right here. So I know it's going to be even on both sides. So we're going to go half of the distance on the right and half of the distance on the left. So if I take 11.2 and I divide that in half, we'll get 5.6. And I don't know what the y value, well, I do know what the y value is, right? Because we decided to make this solid line our x-axis, right? That's going to be 0. So that gives me one of the points right away. And, you know, that should be fairly helpful, right? Okay. The first question on here is find the distance from the x-axis to the top of the circle. Okay. So what we want to do to begin with is see if we can find this distance here. Okay. And again, in a lot of these problems, there's more than one way that we can go about setting things up. So if you had a different process and it works, then go with that. You know, I can think of probably at least 3 different ways to start this problem. I'm going to try to go with what I think is probably the most intuitive, not necessarily the fastest or easiest, but like what's the way that I think I would be most likely to think of just looking at this. And my thought is I want to get equations as quickly as possible, right? We're a lot more used to algebra than geometry typically, especially when things get complicated. And so what I want to do is see if I can start making some equations. So the way that we can write equation of a circle, for a circle centered at the origin, right, you get x squared plus y squared equals r squared. If it's not centered at the origin, we can just either subtract on the x or subtract on the y to shift things over. Okay, I know in this case my r is 14. I don't know how far down my circle is shifted though. Okay, so once I answer that first question, I'll be able to figure that out, right? Because I know from the center to the top of the circle is 14. If I subtract off that distance, then I'll have how far the circle is shifted down. Okay, so I think that's why we need to figure out this first part first. Find the distance from the x-axis to the top of the circle. Okay, so we need to do that in order to find the equation of the circle. Okay, that seems fair. So how do we go about doing that? How do I find this distance, right? And like we gotta think of like what's an intuitive or obvious way to do that. So maybe one thing that we could do is we could say, well, I know this circle has, you know, some equation to it. Right? It's shifted down by some amount. Maybe I'll call that amount, I don't know, we'll call it A. So then this would be x squared plus y. Because I'm shifting down, I want y, you know, plus A squared equals 14 squared. Okay. But I know a point on the circle. I know if I plug in 5.6 for x, then I'll get 0 for y. Okay, so 5.6 squared plus a squared equals 14 squared. So I can just subtract and take a square root to get that value for a. Okay, so I get 12.831. So I kind of did things maybe in a slightly different order because now I have the equation of my circle first and this distance, you know, second. Okay, but you know, like I said, there's other ways to set it up. So if I want to find that distance, if my value of a is 12.831 and this total distance is 14, then the difference is this from the x-axis to the top of the circle. Okay, so 14 minus 12.831 gives me 1.169. Okay. Right, so that's my first question. And then the equation of the circle is going to be x squared plus y plus 12.831 squared equals 14 squared. Okay. Next, find the equation of the parabola. We want to do this as simply as possible. To find an equation of a parabola, one way to think of a parabola, I think the most common way that we think of a parabola is we think of something like, oh, I want to avoid a. Normally we think of like ax squared plus bx plus c equals 0, right? That's a basic parabola. That's going to be kind of hard to work with, though. What I want to take advantage of is I know one of its x-intercepts. And actually, that means I know the other one, because because the vertex is up here, right? It's on the axis. I know that this other point is going to be negative 5.6 comma 0. Okay. So instead of writing this as, a generic parabola ax squared plus bx plus c, what I'm instead going to do is I'm going to write it as some constant. I don't want to use the a, b, and c because I don't want to be confusing. So we'll just use d. And then I can multiply by its x-intercepts, right? So x minus x1, x minus x2, right? And instead of equals 0, maybe we could write like equals y. So what I'm essentially doing is I'm just writing the factored form of the parabola instead. And since I know what the factors need to be, that's going to be a little bit easier, right? So I have d times x minus 5.6 times x plus 5.6. And I know this point, right? This point is 0, comma 6.63. So what I'm going to do is plug in 0 for x. Oops. And sorry, not y. And y is 6.63. Okay. So then I can use that to solve for d. So I have 5.6 times negative 5.6 gives me negative 31.36. So when I divide those, I'm going to get a negative 0.211. Okay. So my equation of the parabola is y equals negative 0.211 times x minus 5.6 times x plus 5.6. And this is a perfectly good equation of a parabola. I don't need to FOIL it all out. However, I think once I need to integrate, I'm going to probably have to FOIL it all out. Okay. So now to find the area, my intersection points are negative 5.6 and positive 5.6. And then I'm just going to take the equation of the parabola. I've already solved that for y. And then subtract the equation of the circle. We want to be a little bit careful here and make sure that I solve for y. Okay, so I have to do a couple steps of work. So looking at the circle, if I start with x squared plus y plus 12.831 squared equals 14 squared, I want to get y by itself, so I start by subtracting. And, well, I'm going to do two steps here. I'll subtract and then square root. Okay, and then I subtract again. Okay, so there's my y equals. Okay. So there I have set up my integral. Okay. And I don't think I want to go through the mess of integrating that. I think setting that one up is the difficult part. For integrating, we just kind of have a mess of multiplying everything out. All right. Any questions on this one? Okay, I realize that was a question that you didn't ask me just now, but somebody asked me, and so I wanted to make sure it got answered. Okay, let's move on now to section 5.2. I said 5.2. I meant 2.2. Okay, which question out of 2.2 did you want to look at?
Yeah, so when I was going through them earlier, I was having issues because I would get the right answer just by finding the area, like the volume, but I know that's not how you're supposed to do it. You're supposed to use the integration method, but I could never get the right bounds. I didn't know if you're supposed to go from the origin to the length of the side or if you're supposed to do some other way. I just couldn't figure out the definite integral bounds, like the bounds you're supposed to use.
Okay, so should I just pick one?
Yeah, just pick any of them.
Okay.
Yeah.
So find the volume of a pyramid with height 18 and with rectangular base with dimensions 6 and 8 using integration. So I'm going to give like a rough attempt at sketching this. It's three-dimensional, so that's not, certainly not ideal for me. But so here's my square base, right? And then the pyramid goes up from here. Okay. So it has a height of 18, and one of these is going to be 6, and another one is going to be an 8. Okay. And we want to find the dimensions using integration, right? So like you said, right, we have formulas for area of a pyramid. And one of the things that we're going to be doing later is looking at, well, how do I get formulas like this? Could I, where does the formula for area of a pyramid come from, and could I derive it? And the idea is, well, yeah, I could figure it out using integration, but not vice versa. So we want to be able to say, can I do this without using the formula for area of a pyramid? Can I set up an integral that will do this? And how do we even do that? So let me first, I want to show you what our setup is. That's not what let me pull up our book real quick. What I want to do is I just want to look at how do I even set up these volume integrals, and I want to sort of walk you through what our process is. Okay, so let me just turn that off. Okay. In 2.2, we look at like volumes by slicing and stuff like that. But first, what we want to do is think about like, generically, how do I find volume? Okay. And the idea is, one thing to keep in mind when we talk about a cylinder, we always typically think of a round cylinder, and that's what a lot of our examples will look like. But really, in math, we can think of like any sort of two-dimensional region as long as it's, repeated throughout. Okay, so a cylinder is defined as any solid that, takes the same shape and sort of just repeats it along the axis. Okay, it could be tilted in different directions and stuff, but as long as, like I'm repeating the same shape. So like this is, mathematically speaking, also, same idea, right? So, okay, what we want to do when we think of a volume is break it up the same way that we broke up area back in Calculus 1. And the way that we broke up area was I said, all right, we have this region. We're going to chop it up into very simple shapes that I can easily compute the area of and add those up. So we do the same thing with volume. We say, okay, I'm going to take this three-dimensional region and I'm going to chop it up into simple shapes. And the simple shapes that I want to chop it up into, when we talk about, slicing and stuff like that, that can vary a little bit. But we want to chop it up into a very simple shape. All right, these like, cylinders. and we approximate it, right? So when I think of, let me see if I can get a nice picture here. I don't really want to use an area of revolution for this. Okay, I guess this is the best picture that we have to work with. This is kind of the same idea as like our pyramid, right? So we're going to take this solid and we chop it up into pieces. Okay, and we aren't going to find the area of these pieces exactly because that's just as hard as our original problem. But what we can do is approximate them by turning them into boxes. Okay, and what we're going to do is we're going to take like each of these three-dimensional objects and just think about it as instead of curving down, it's just going to be straight over. And that box will be close to the same area. And if my region is really thin, then it doesn't curve down by very much at all. So the thinner I make these slices, the better that these boxes will approximate. And so if I use infinitely many, I get the exact area. So that's what we're looking at here. The volume is going to be, if I just take the area times a little bit of thickness, right, that's like a box, and I add up all of those boxes. Okay, so if I take infinitely many of them, I'll get the exact area. So what we're doing is essentially integrating the area of my region from start to finish, right, from A to B. Okay. So now let's look back at our pyramid here and say, well, how do I do this? Okay. So I want to think of like if I were just to take this thing and slice it up, right? So just think of this as like a three-dimensional slice. Okay, as being an arbitrary slice. Okay, then the face of that thing has some area. Just turning that on its side here. Okay, so then this face has an area, A of x, and it has some thickness to it, which is our dx. That's going to be our differential. Okay, so in this case, my x-axis is going up, right? We'll think of this bottom part as being x equals 0. Okay, so what I want to do is I want to say for any arbitrary slice, what would be the area of that face of that slice? Okay, and I know that when x is 0, I just get this 6 by 8 rectangle. Okay, when x equals 0, right, I have a 6 by 8 rectangle. Okay, when x is 18, I don't have one anymore, right? We get nothing. Okay, so how do I get like a slice in between? Well, I know that, you know, these are lines. It's kind of going linearly up, right? The width and length, I guess, of my sides are decreasing linearly from 6 and 8 to 0 as x goes from 0 to 18. Okay. So what I want to do is, you know, think about that proportionally, right? If I go up by a certain amount, right? Let's suppose I go halfway up, then I should be halfway. It should be like a 3 by 4, right? So you could think of that as being proportionally as high up as x has gone. That's how much we have shrunk our dimensions by. Okay. So how do I write that? Okay. So when x is 0, I get my full 6 by 8, and the area there is 6 times 8, or 48. When x is 18, my area is 0. And we're just going proportionally up, right? So if I go halfway up, I'll be, you know, half the length and half the width. Okay. So my length okay? It starts at 6 when x is 0, and it ends at 0 when x is 18. So I could think of this as being like an 18 minus x. I'm sorry, not 18 minus x. That's kind of like the idea that I want. I want to set up like this counting thing, but when x is 0, I don't want it to change at all. Okay, and when x is 18, I want to have wiped that out. Okay, but what I want to be doing is multiplying by something that's 1 or less. So I want to think about this, going up proportionally, and kind of a standard way to do that in math. I am going to have like a subtraction here. Okay, but maybe I want to rescale it, right? If I take my x going from 0 to 18, if I divide that by 18, then I'll be going from 0 to 1, and that's the scaling that I want. Okay, so I'm going to take my x minus 18 and divide by 18. Okay, so now when x, oh, I'm sorry, I want 18 minus x. Okay, and let me show you what's going on here. 18 minus x, when x is 0, I'll get 18 over 18, which is 1. So I'm multiplying my length by 1, and I'm good. When x is 18, I'll get a 0. Okay, and so then I get my nothing that I want. And it's scaling up linearly, right? So like when x is, say, 9, I'll get 18 minus 9, which is 9. And then 9/18 gives me exactly half, right? So that's kind of what I want. So what I'm doing is I'm sort of creating a linear function. Okay. I have to go backwards. This is 18 minus x because when x is 0, that's when I get my full area, right? Okay. And then I divide by 18 to rescale it. Okay. And the width is the same way. Okay, so then my area function a of x is just length times width. So 6 times 18 minus x over 18 times 8 times 18 minus x over 18. That's my area function. Okay. Okay, so I'll just write that maybe a little bit more simply. So that's 4/27, and then I have 18 minus x squared. So then the volume, I'm just going to be integrating that function. I'm going to start when x is 0 and end when x is 18. So that's how I can set up the volume as an integral instead of just using the volume equation. Okay, does that make sense? Here's the thing.
Yeah, it does.
I understand that like this process seems really complicated. Like if I just have a pyramid, nobody's going to do this. The idea is to start with simple shapes because it makes the setup part a lot easier. And I know that this was already a little bit complicated, but like once you understand this idea of using these linear, functions to decrease down proportionally, right? Then you use that in a lot of different problems. Okay, so like if I looked at like the next one, find the volume of a right circular cone with height 36 and base radius 9 using integration. And I'll just set this one up a little bit faster. Again, we know volume of a cylinder, and you could just compute that right away. Okay, but if I think of saying, all right, I want to make some, what would one arbitrary slice of this thing look like? If I pull that out, right, I get this circular disc with this tiny little bit of thickness to it. Okay, that thickness is like my differential dx, or you call it like the delta x, and then this would be the area of the face, and that doesn't change as x is going up. Okay, So my area function here would be constant, right? So if the radius is 9, right, pi r squared, so that's 81 pi. So my volume is going to be the integral of that area function, 81 pi, going from x equals 0 up to x equals 36. Okay, and this one is a little bit easier to work with, right, because I'm integrating a constant. Okay, so I get 81 pi times 36 minus 0. So we get 81 pi times 36, right? What's the formula for volume of a cylinder, right? It's pi r squared h. So I have pi r squared h, right? And you can see that they line up. It's a lot easier when the area is constant. Okay. And so then it makes it easier to see how to set up, things like this where, okay, every cross-section parallel to the x-axis is a triangle whose height and base are equal. The idea there is that they're telling you how to set up that area function, that a of x. So I have a height and I have a base. The area of a triangle is, 1/2 base times height. Those are equal to each other. Okay, so let's look at question 8. Oops. Okay, the graph above shows the base of an object. Compute the value of the volume of the object given that the cross sections perpendicular to the base are squares. All right, so what we have is I have an object that's coming up out of the page here, and the cross sections perpendicular to the base are squares. So if I wanted to try and draw that, you don't have to draw this, certainly. But just to give you an idea, it says cross sections. Let's see, cross sections perpendicular to the base are squares. So, like if I look at this piece here, that would be like the base of my square coming up out of the page, right? So then I'm going to get a square that comes up with that same height. But over here I have a smaller square, right? Okay. And up here I have this really big square coming out of the page. Just draw that carefully. Okay. And it's going to be like that for all of these pieces when I get to the end. So this is going to be, it comes down to a point here at the left, and it's going to get taller and taller until it hits this point where it gets at its widest, and it's going to stay the same. Okay. If I want to find the volume of this thing, what I'm going to do is, I'm going to use my x-axis here. Okay. And I'm going to say the volume is the integral of a of x dx, right, from a to b. I'm actually going to set this up by looking at two separate pieces, because my area is going up along. Here, let me use a different color. Actually, let me just, I'll use a different color here. As I move up along, as my x increases here, right, my squares are getting wider until I get to this point 3. From 3 to 6, the area is the same. Okay, so I'm going to break this up into two different integrals. I have the integral from 0 to 3 and the integral from 3 to 6. Now, from 3 to 6, remember that my cross sections are squares, and the base of the square is always going to be 6, right? Because it's, from the top to the bottom is 6, and it's a square. So the area is 6 squared. Okay, so that piece is going to be easy, right? That's no problem. I just need to figure out for this first half, okay, what's going on, right? And so I can label, clear this out to make it a little easier to see. if I just think of what does one slice look like, okay, I'm going to call this S for the side of a square. Okay, so my area function is a side squared. And to figure out what that side is, well, if I figure out the equation of this line will tell me the height. I just want to double that height. Okay, this is a line that goes through the origin, and it goes through the point 3, 4. So the slope of the line is change in y over change in x, so 4/3. So y equals 4/3 x, right? Or I should use point slope formula, but y minus 0 is 4/3 x minus 0, right? So y equals 4/3 x. So that's half of the length of one of the sides, okay? So S is going to be double that, 2 times 4/3 x, or 8/3 x. And my area is going to be that thing squared. So I'm going to get 64/9 x squared. Okay, so now my volume equation is the integral from 0 to 3 of 64/9 x squared dx plus the integral from 3 to 6 of just 36 dx. Okay, and then we integrate away. I get 1/3 x cubed from 0 to 3. Here we just get 36x, where x goes from 3 to 6. Oops. So my constant is 64/27, and then I have x cubed, so 3 cubed minus 0 cubed. And over here, when I plug in, I'll just get 6 minus 3. And we compute away and get our answer. Right. No, never mind. Don't do math in your head. It's a bad idea. We'll just compute away from there. Okay. Oh yeah, and I'm adding, not subtracting. Anyway. Does that make sense now? Well, maybe I rushed part of it. Again, the key is we're looking at the volume as the integral of that area function. We just want to break it down into pieces. The shapes are squares. The area of a square is the side squared. So we say, okay, I got to figure out what's the length of a side. If I can bring that back to an equation, right, I do that. So I say, well, this y value is half of the side. So I find the equation of that line, double that to get s, square that to get a, and then I can integrate away. Anything else from 2.2? Okay, any questions from 2.3? So yeah, again, you don't have to draw stuff by hand, but it's sometimes helpful to see. Although I think I think for a lot of this stuff, the three-dimensional graph is just can be too confusing to try and pick apart and get information from. You just want to break it down into its pieces. Okay, if there aren't any questions on 2.3, then I think that we're good to go here. If you do have questions as you're going through and finishing the homework, definitely email me or drop into office hours or something like that, and we'll get those answered. Homework is due tonight. Yes. If you, first week, we didn't have class on Monday, so I guess in a way it was kind of a shorter week. If you're running into problems finishing it by tonight, just let me know or use a late pass tomorrow, and that's fine. But if you're running into problems on anything, definitely email me. And don't be worried about using a late pass. What's going on? Don't be worried about using a late pass to finish it up if you can't get it done. It's better to make sure that you can do all of the problems than to rush through. So yeah, knowing it and getting the practice done is far more important than making the deadline. But yes, the due date is tonight for week 1 homework. And then after class, I'm gonna put out the week 2 homework and notes and stuff, so you can start. Once you finish your homework, you can start looking at stuff for this week, arc length and stuff like that. All right. So what we'll do is on Wednesday's class, we'll start talking about this week's material a little bit, and I'll try to point out some things that I think could benefit from a little bit of extra attention. But I think that we're probably good for today, unless anyone has any other homework questions you want to look at. Okay, if not, I think that we are probably good for class today. Thank you for showing up to class.